And we'll start off with where we left off last week. So last week, right, we talked about the Earth's gravity well, or the escape velocity. Okay. And my OneNote is a bit weird. Okay. Close everything. Okay. So when it comes to this gravity well, right, your Earth is trapped or earthbound, but there are different parts where we can float a satellite. Okay, so we're going to start from the top, where let's say we are to assume that you have a satellite that is already in orbit. So I have Earth, okay, and there is another satellite here floating about, traveling in orbit. So this is not an unfamiliar picture. It's throwback time. Satellite is mass small m. The Earth has a mass capital M. So a few things are happening at the same time. Number one, there's a gravitational attraction between these two things to allow the satellite to sit in the orbit. So this one, gravitational force provides centripetal force. So the first idea. And from here, we can obviously fill in what we already know, which is the Newton's law of gravitation equation, equal to mr omega squared. So from here alone, we have already done quite a lot of past year questions. This is level 1 mark, correct? But from here, I can also find, I can also use mv squared over r. Okay. So when I equate this to mv squared over r, I will notice something pretty interesting, where my v squared is equal to gm over r, or v is equal to square root of gm over r. This is what I call the orbital speed. The speed where this satellite is traveling, a satellite is floating in this direction, this is the speed. Okay, so it's moving in a circle like a circular orbit. Can calculate using this. And r is obviously the distance measured from the center. This is your r. Okay. But when it comes to energy, which is the third and fourth pillar, by the way, let's say I want to consider the total energy of the satellite. Total energy of a satellite will be the sum of kinetic energy, because the satellite is moving, plus potential energy, gravitational potential energy to be exact, because the satellite is not at infinity, so there's definitely GPE. So maybe I find an expression for KE first, because I have V squared. So half mv squared. And this kinetic energy can be written as half m. V squared is gm over r. Okay. V squared is here. I can substitute here. So when I rearrange all, I get g mm over 2r. Okay. Teacher, why it looks so like the GPE one? Because they are both energy, so they should have the same physical quantities, same dimension, same units. Okay, so GPE here will be equal to G mm over r. Okay, we're going to add them together. So hence, total energy is equal to GMM over 2R plus negative GMM over R. You see on the left side, the first term, you have GMM over R. GMM over R. Then here also GMM over R. Can take out, right? So if we take out, what we have left is 1 over 2 minus 1. And this is negative 2R. So I don't know how your brain works, but my brain, whenever it sees like similar equation like this, right, it just want to yeet out of the subject. Which means to help my brain feel a bit safe in its understanding, I must know the origin of the equation. That way, if my memory fails me, I can always go back to the drawing board. What provides centripetal force? Because that was the link for me to find the value of V. But if you're a type where, I can remember, I'm a memory champion, go ahead, okay? But you also need to know the proof. So they can ask you the proof for anywhere between 2 to 4 marks. Out of the 100 marks you wanted to get for your A2, 2 to 4 marks. So I have to grind a bit. Okay. So a few things about this. Number one, I want to be able to graph all of this so that it makes sense to my brain. Okay. So let's say I have a satellite. This is Earth. Okay. So I'm going to draw the graph of energy against distance. This is E, this is R, this is Earth. No? So my satellite can be anywhere. Now it's here. It can go away towards wherever it is. So if I want to draw KE graph, it's very straightforward. It is GMM over 2R. So this is my kinetic energy is positive. So I'll probably get a graph that looks like this. Positive, but 1 over R. So like that. This is KE. Okay, go up until you are lazy to draw. No space. Okay. GPE is negative. We know why it's negative, right? This negative here is to show us that the gravitational field is attractive. So the reason why the satellite is here to begin with was because gravity did the work to bring it here. Gravity attracted us to it in the first place, all the particles. So that's why it's here. That's why your GPE is negative. In fact, it will be negative double of this. So I should actually draw something that looks like double of this graph. Does that make sense? Double or almost double. It's a sketch now. Okay, get the point. Double GPE. Because GPE is negative GMM over R. Total energy would be the green graph plus the purple graph. Okay, which means the total energy will be symmetrical to this green graph. ET. Okay. Total energy. Okay. Question. When my satellite's R increases, let's say I move my satellite to higher orbit. So let me write here. If the radius of the satellite, not radius of satellite, the distance of the satellite from the center of the Earth, here to here is your R. If R of satellite increases, what happens to your KE? KE actually decreases. You look at the graph. Okay, so KE decreases. You can tell from your equation that when R is bigger, this KE will be smaller. So this one is the most straightforward one. But when there is a negative sign, there is sometimes a slight knot in the brain. Because when there's negative sign, when we say something increase or decrease, for physics, right, the plus minus sign doesn't show magnitude at all. So in maths, let me ask you, in maths, is negative 100 less than negative 50? This is correct in maths, right? This inequality. In physics, right, negative 100 is greater than negative 50 and all the maths teacher loses their mind. Do you know why? Because this negative doesn't show me magnitude. The negative is something else. This negative could be direction. That was the first time we used plus minus sign in your physics. Go to the left, go to the right. It could be charge. I don't know. Negative 100 coulomb is bigger, it's more charged than negative 50 coulomb. Right? It could be work done to show me who is doing the work or what is the work done. So in this case, this negative, it is just to show magnitude. Okay, so you don't know. So you need to look at the graph. Okay, but generally speaking, to help us with this, you don't know, so sketch the graph, okay, because the graph can tell you the trend. So right now, if R increases and we look at this GPE graph, you can see that your PE is actually increasing. Okay. So remember the negative, it becomes a smaller negative number. So from the perspective of energy, it is still increasing. So sketching out the graph can help, or GPE will increase. It is less negative. Less negative. Okay. So it's not as straightforward as just comparing absolute numbers. Sketch the graph. Okay. Number 3, total energy. Strangely, total energy is not conserved, you know. There's energy lost from the system. So your total energy still increases. So total energy is not conserved. So a note here, energy is not conserved when you move the satellite into higher orbit. That's why we need a rocket. Extra energy needed. Right, let's try some questions. String this a bit so we copy. Especially work done now. Work done is the one that will twist the brain a bit. So give yourself a brain time used to a new way of looking at science, especially for physics. But for maths, can still stick to the negative, means the other side of the number line. Let's look for an example. By the way, right, in your Google Drive, I have started uploading the new syllabus in your notes now. So if you're referring to your Google Drive, you can print the new one. I got labeled new, besar, big there. In the topicals. New. But the syllabus is the same, so the question will be the same. Don't worry. Okay, let's try a question. I will leave this one to you because I find this as a useful exercise when I know I need to remember the proof. I will normally just take a break, 24 hours, or have to remember a mechanism. I take a break and then I come back, I pull out a piece of paper to derive from scratch. Because I memang jenis yang tak boleh hafal. Okay, so if we look at this one sets up the same drawing as I did. Okay, so your satellite MS, okay, they use different symbols. Okay, so this is your Earth. Satellite is here in circular orbit, radius X. Same idea. Okay, maybe your drawing also as chacha as mine, but it's okay. So this is capital M, this is small ms. Show that the kinetic energy is this one. 3 marks. So I did 2 steps, right? Step 1, I find the centripetal force equation and I equate it to find orbital speed. Step 2, once I have orbital speed, I sub into half mv squared. Once I substitute into half mv squared, I get the equation. So do yourself, 3 marks. State the GPE in terms of GM, MS, and X. Well, just writing the equation. Very nice. Derive an expression for total energy. So write this equation and then write this one by showing the summation. So show the summation. So all okay, no problem. So I leave it to you. 6 marks. So the entire proof I show you just now is 6 marks. Nice. Okay, so let's look at B though. B here, it says that a small resistive force acting on the satellite causes the radius of its circular orbit to change. Ooh. Okay, the radius of the circular orbit will change. Using your answer in A, so all the equation that we have derived just now, state for the satellite whether each of the following quantities increase, decrease, or remain constant. Small resistive forces. Maybe it could be the friction inside the engine. Maybe there's some solar wind. I don't know. Something happened. Something happened to resist the motion of the satellite. So what happens to the total energy when there's a resistive force? You think about this. It's like if got resistive force, which is something like some form of either internal friction of the engine or the flying mechanism, then the total energy will decrease, right? Because some friction, something happening, I don't know what happened, decrease. In fact, there's always some hidden resistive force that you don't know about. So decreases. So now you tell me, what do you think happens to the radius, the potential energy, and the kinetic energy? So I will give you the equations if you need it. Kinetic energy, and I remember only because I just derived, okay, or maybe I derived too many times this week already. Potential energy is negative, it's the Ch13 life. Also how I studied for my STPM last time. When my member haven't studied yet, my friend haven't studied yet, I just go and like, if you haven't studied yet, come I teach you. And then I scully goose, I do my own revision in my brain. I can draw the graph, but I think you can visualize, learn to visualize the graph on your own. So let me know. 2, 3, and 4, give you a few minutes. If the total energy is less, your satellite is losing energy. What happens to the radius? What happens to the PE? What happens to the KE?
The radius decreases.
Radius decreases. Okay.
The potential energy also decreases.
Mm-hmm.
And the kinetic energy increases.
Okay. So let's see if we can confirm that in our brains. If the total energy decreases, because this total energy is negative, right? Total energy looks like this. So if this one is to decrease, it means that I'm traveling from maybe here to here. ET decreases. So your radius, your value of R has decreased. Maybe this R1, this is R2. So once you know radius decreases, then you can just plug it into the other equations. If this R is smaller, this EP is a negative number of greater magnitude. So it still decreases. And then your kinetic energy will increase. Great, good job. Okay. Other formats of questions involving this would be to give you the actual scenario itself and ask you to perform some calculation. Okay, so we're going to look at a question from Feb March 16. Let me screenshot this. Feb March 16, paper 4. Page 11, I believe. So to begin with, you are asked to state Newton's law of gravitation for a total of 2 marks. 2 marks. So first mark, right, just as a recollection, is you write down the statement of force is proportional to the product of masses. Product of masses. And inversely proportional to the square of the separation of the masses. So there's a formal statement in your notes lying around somewhere. But the main point here is also very important to remember. This is the attractive force between 2 point masses. So this is normally the point that students forget to write, and then they lose 1 point. Get it? Right. It is about point masses. Because we assume all the mass is concentrated in the center and we measure all the distances from the center. Okay, so we start with the same idea. We got a satellite, circular orbit, radius r. At this point in time, you're like, wow, I think I tepu already. I see this, I know what to do. Good. Grind the past year until most chapters achieve this level of saturation. So you want to show this equation, and I think I've showed it in the notes already before, right? So the important, this is 2 marks. I don't know why I cropped away the marks. The important marks to show, number 1, is centripetal force is equal to gravitational force, and then you work your way to V is equal to this one. So you start from here, and then you show your right substitution, basically mv squared over r here, whatever this one is. You get 1 mark, leading to this one. Nice. Okay, so I want to do this one. You have 2 moons, A and B, with circular orbit about a planet. Do you know any planets with 2 moons? Let's test people's either astro knowledge or fiction. Our red planet Mars have 2 moons. Jupiter has 69, but that guy is a show-off. So our neighbor has 4. Okay. So they have different periods, A and B. Determine the ratio of VA over VB and TA over TB. Okay. And then the planet spins about its own axis with this angular speed. And then A is always above the same point on the planet's surface. Determine the orbital period of B. Okay, this one, oh, I know why in my brain I mapped this as an energy question, because I will ask students to transition in your orbit. But never mind, you can still do this. So we have radius, VA, VB, TA, TB. Okay, and you are asked to calculate the ratio of VA over VB and TA over TB. Okay, we do have an equation proven here. So I'm going to use it. Square root of GM over R. And from here, I know V is proportional to R. So I can go VA over VB is equal to RB over RA. Inversely proportional, so I flip it. So this will be 2.2 times 10 to the power of 10 divided by 1.3 times 10 to the power of 8. Then to find TA and TB, I have the ratio that I would like to use, like R and V. I could invite new ratios, but I would prefer not to. So maybe I should modify the equation a bit. So the only one that I know is omega is 2 pi over T, right? But also, I know V is equal to R omega. So I can substitute, right? Can substitute, put them together. So I have V is equal to R 2 pi over T. 2 pi is a constant. So I can say VA over VB is equal to RA over RB. T is at the denominator, so I'm going to flip it. TB over TB. Yeah, rearrange it. Of course, this one is a bit risky if you're not really also that. Because VA over VB is RB over RE. Correct. Okay. Inversely proportional over R. Okay, let me rearrange first. VA over VB is RB over RE. If you are a bit apprehensive in writing this way, so your examiners are a bit lost, then you just mention here 2 pi constant. Hence, V is proportional to R over T. But also, when I move on to this line, what I'm doing is VA over VB, which is this one, is equal to RB over RE. Then. So after some rearranging, I get TA over TB is bracket RA over RB squared. So I just take whatever answer here and power 2. So generally speaking, this kind of celestial studies, right? Man has been doing it since quite a while in history, I believe. That's how we tell the calendar or the years. But no, this is 169. Can put 170 also, no problem. 2.86 times 10 to the power of 4, or 2.9 times 10 to the power of 4. Okay, I think part 2 is fairly straightforward. Because part 2, you are given the period. This is the omega of the planet, which is the same because moon A is above the same point as omega of the moon. That means period of the planet is the same as period of the moon. This is moon A. And we have the ratio of TA to TB right here. So can substitute inside and then can find TB. It's a pretty beefy question, as in like it has quite a lot of marks for something pretty straightforward. Right, I'm closing stuff because my computer is very laggy now. So give me a sec to off all the things, including this. Okay, I have questions. If you don't have anything you want me to address first? Okay. Anything you want me to address? Any mistakes, any calculation error, substitution error?
Miss Lee,
Yes.
wouldn't it be V equals to square root 1 over R? So,
Yes.
okay.
All right. Waiting. Okay. Square root here. Why do you think I put everything in one screen? I just want to show what happens if you're like, oh no, this happened. Okay, like, you don't worry. You notice that I barely needed to rub anything. And because this is not, if you write within the space, the Cambridge people are okay, 30. So you just cross out your answer there and write 30. This one here, like, same thing. But here needs a bit of adjustment. Okay, so let me rub this VA first. This VA here is square root, right? So if you bring up, this is power half. You imagine this one is power half, you shift up, then this is power need to change a bit more. Power 1 plus power half. So it's power 1.5. Okay, so the 2 become 1.5. This one become 1.5, and then you cancel off this one. You cannot bring correction tape, what? Okay, so don't go and, oh no, everything wrong, then rub furiously and make a hole in the exam paper. This happened to some people too. Okay, by the way, it's not 169, it's 13. Okay, so these are all cancelled. This will be 13 power 1.5. Consult Casio, your calculator. Is it 13? RA over RB. Yeah. Oh, that I should substitute, right? Okay lah. Cancel everything. You can put in RA over RB, but I don't have RA over RB now. As in, I don't have the ratio of RA over RB. This one is gone. It's okay. 1.3 times 10 to the power of 8. 2.2 times 10 to the power of 10. Power 1.5 or 3 over 2. So 4.54 times 10 to the power of -4. So whenever you see ratios, right, especially when it comes to planet objects, and it is so big, this one was very big, right? Immediately, you'll be very suspicious already because one will move quite fast and then the other one is just slowly crawling along at 20,000, 28,000 times slower the period. That would be a bit weird. Right, where are the marks? Let's use green pen for this. If we see this or this, you get 1 mark already. And then the final answer leading to 13 is 1 mark. And then for this part, if there is V is equal to some format of this equation or this proportionality relationship, you get 1 mark. And then your ratio is written correctly with correct substitution. So here would be 1 mark. And then the final answer is 1 mark. So I will know whether your ratio is written correctly based on the final answer. Normally when we mark, right, we will look at the final form. Normally, and then if let's say you don't get the answer, and then I will trace back to try to see if I can find the mistake. Okay, so make sure there's a step where you show the input of all the values, because sometimes you can put in the right values and press your calculator wrongly. So that will help you not lose the second mark when it's a 3-mark question. When it's 2 mark, that 1 mark can be at the equation. Sometimes it can be at the substitution. Most of the time it's in the substitution. Okay. So just to give you an overview of what we've covered so far, which by the way, right, this means, sorry, this one needs to change, okay? You got this one already, ma? TA over TB is this. So TA over TB is 4.54 times 10 to the power of -4. The TA is omega is 2 pi over T. So 2 pi over omega. So 2 pi over 1.7 times 10 to the power of -4. So you can find TB pretty easily. All right, so I'll leave that to you. I believe the answer for this one, let me ask my best friend. And by best friend, I mean paper.sc. This is 8.1 times 10 to the power of 7. This is 3.70 times 10 to the power of 4. Okay, because this is radian per second. Okay, some interesting simulation to look at before we round off this chapter would be about the energy. So the energy graph that I drew is this one. Okay. And depending on where the satellite is, you can see as we trace closer and closer, when the radius decrease, the satellite is actually moving faster because the KE will decrease compared to here. Satellite is moving slower, decrease, the satellite will move faster. KE increases. But your PE is dropping because it's moving closer to the planet's surface, and so is your total energy. So it's a bit like a Goldilocks situation where I need this satellite to be able to have just the right speed. If it's too fast, it will fall towards the ground because the centripetal force is not enough. Okay, if it's too slow, then other things will happen. Let me show you what I mean by that. So this is a satellite. It's the orbit. I cannot zoom in. So I'll put up the simulation together for you in Discord later. Most of the satellite is in low Earth orbit. Your Miasat satellite from Malaysia, the satellites from the communication satellites that allows you to watch the Olympics. Right? Here. So if you look at the energy, right, kinetic energy is positive, potential energy is a big negative, and you add the first two bar, you get this one. And this is the orbit. But what happens if I change the energy? So what I could do to change the energy is to pause this one. And okay, tell me what to change. We want to yeet away from this Earth. Maybe I'll change the speed. So I'll add the speed. Notice as I add the speed, I'm making the total mechanical energy less and less negative. Notice that? Okay, still negative, but let's play. Let's see what happens. So satellite now does something pretty strange. I mean, it goes further away. The force is not 90 degrees anymore. This is GG. It's not 90. But it doesn't feel like it's escaping, or will it? Some form of acceleration going on. It's like it's slowing down. You can see the dotted, the point here is to show ping. So here the points are very close, like your ticker timer, it means it's slowing down. But then it's accelerating again. And then it's accelerating very quickly. So it takes the shape of an ellipse. This elliptical orbit is when your speed is faster than that orbital speed, the square root of gm over r. This is faster. Okay. But to get the elliptical orbit. You can see here is very slow, here is very fast. All this we will study later if you do more physics. But what we are talking about now is maybe I want to increase my speed until the total mechanical energy becomes positive. Okay, what happens to us right now? Satellite be like, well, it was nice knowing you, Earth, but thanks, but no thanks. Bye-bye. So the satellite will actually begin to escape. But I need enough energy. So it's not just about overcoming or exceeding the centripetal force. I also need to think about the perspective of the energy. When we started this whole story, the energy was negative. Very, very big negative, thanks to the potential energy. In order for it to escape, I need to be able to give it enough kinetic energy such that it overcomes the negative potential energy and then escape. So this is the escape velocity. So if we look at last week's notes, exciting stuff, that one will just go on to infinity and beyond. But if we look at last week's notes, right? Somewhere here, there's a derivation that I didn't show you, which is the escape velocity. So we're going to go back and do that. It's a form of completion, of saying bye-bye. It's still going to travel, you know. I'm just going to leave it here, okay? We'll see where it goes after a while in class. Just leave it there. Okay. So number 3, we're going to look at escape velocity. So this means the satellite or the object travels to infinity. It's a bit like a toxic relationship, lah. You know, you see some people, they date not the best people, and then they always get back together with them. And you go, why lah? Why you go back to the person? The person is not good for you. But it's the gravity, you know. So you need to give your friend a bit of a boost, escape velocity. Okay. So it means that the KE of the satellite or the object, you know, any object of the rock or whatever, must be enough to make the total energy positive, or at the very least, 0. Okay, so K of the object, or rather the change in K of the object is equal to the change in GPE of the object to infinity. Okay, so the kinetic energy, you can put half mv squared for now. And the change in GPE from the object is I had gmm over r negative, and then I'm bringing it to infinity, which is 0. So I will take 0 minus this final minus initial. So this one is GPE at infinity minus GPE at r, or the radius r. Okay, also we can, I guess, do a bit of cosmetic work. Half mv squared is g capital M small m over r. This m can cancel away, and you are left with v squared is equal to 2gm over r. Or v is square root of 2gm over r. This is known as the escape velocity. Compare this with your orbital velocity. V is equal to square root of gm over r. So the factor that makes them different is just root 2. Just root 2. That's actually quite big also. Okay, so of course we can put in the numbers here, but I think we calculated it last time. You actually need a lot of space, a lot of energy to accelerate. And I actually don't know where the satellite is anymore. It's gone, it's still increasing, but it's gone, it's gone. Okay, to simulate this, or to show you what it means to have escape velocity, I want to show you this Einstein way of looking at gravity. As a simulation somewhere. Here. Okay. So during Newton's time, Newton's explanation about gravity or attraction between two objects has been very mathematical. So we can prove this using equation. We can measure the period of any object by looking at the angular displacement and then do some calculation that is similar to what you have done early in this chapter. But Newton was unable to explain why gravity, or come up with a model to try to explain how gravity transfer the force, right? Like for example, we accept that, well, the moon is attracted to the earth, but how does the earth pull the moon in? What exactly is happening? Got tie rope, tali, magic hand, you don't know. You legit just don't know, but you know it behaves that way. It's a bit like we don't really know how coronavirus works. We don't know why certain people get really badly infected, but certain people not really. We know it's kind of related to some risk factors, but there are also people who seem to have the risk factors and seem to be okay. So actually, basically, it's just one big I don't know. So same thing, but of course with a little bit more certainty when it comes to gravity. Until our friend Einstein came along, like, you know, Einstein, that guy with the crazy hair. Okay, like he says that gravity can be visualized like kain, like a piece of cloth that you put on a table. Like this. So because any object that travels in a straight line will travel in a straight line. So this is Newton's first law of inertia. Take a piece of cloth, to pick aside, you roll it, you move in a straight line. No problem, teacher, it's not very boring. Yeah, it's very boring. I agree. But sometimes we put a heavy bowling ball there. That will change the fabric of space and time. So put a heavy bowling ball there. Nah, ta-da. And you can see this part will bend inwards. Now what happens if I put two heavy bowling balls like Earth and Moon? And then what will happen when I put them on the cloth? So imagine this is the dimension of space and time, and I put it on the cloth, poof, they're attracted to each other. Okay? And this warp space and time defects the path of matter. So if you're moving faster than the escape velocity, which is square root of 2gm over r, you can't fall into orbit. Like just now, the simulation that I showed you, you may be deflected a bit, but you can't move in a circle. But if you go slower than the escape velocity, you kind of follow this elliptical circle that I showed you just now, right? Like an ellipse. So a lot of comet, like Comet Halley, they follow this pattern. But the one that we are used to seeing is moving at minimum orbital velocity, square root of gm over r. So it travels in a circular orbit like this. Slow down. It must travel at the exact speed. Of course, this is not the perfect replica of the space-time fabric because there's friction and there's no friction in outer space, but it's close enough. You can observe the circle. Okay. And any object with mass will change the dimension of speed and time. Okay. And you know the Earth orbits the sun, but the moon will also orbit the Earth. So to show you this, I'm going to change the playback speed to very slow. And you observe what happens. The blue color ball is the Earth, and the small white ball is the moon. Moon is going around Earth. Earth is rotating on its axis, but the whole system is rotating around the pink color sun. So or not? Moon is going around Earth. Earth is rotating on its axis. Einstein, big brain. And for example, Newton couldn't really explain why the Earth rotated on its own axis too. We just know it does, but don't know why. You know, it's Einstein's big brain. So those of you who do further maths, right, and you do surface vectors, that is like the baby step to get you to model this in maths. Normal people, it's just a cool demonstration to watch lah. Normal people like me. Okay. So any form of dark energy. So dark energy is the reverse of mass. I put something inside. We observe sometimes light when they travel. For no reason, they deflect away from each other. This is very weird one. So whenever we observe this, we hypothesize that there's another energy that is opposite of mass, but we don't know what it is. So now we're going to look at the formation of our solar system. Okay. And again, I'll put to slow down the speed. So when it comes to our solar system, right, many thousand years ago, when the sun was formed, it has enough mass to begin to attract the rocks in its neighboring surrounding, do work on those rocks many thousand years ago to bring it into the solar system. Some of them are still there. Asteroids, you know, your solar system got the asteroid belt. Those of you who study this or know about this, fun fact. So not all of the asteroid belts, the rocks in the asteroid belts become planet because they're not within the preferred motion. So collision will cancel out random motion. And then the entire solar system has a preferred orbital direction. Everything is spinning on the same plane at the same direction. There's no reverse direction in this scenario. Okay, well, 4 times slower. So what they're going to do now is they're going to model the beginning of the solar system, where they have many marbles and balls. They're going to just release it. So imagine the sun was formed and then there are so many rocks to attract around. First thing he's going to do is going to pull in the rocks that are moving too slow. They'll be all attracted. And then those rocks that are left behind, they will suddenly begin to exhibit a preferred orbital speed. This one that is going in opposite direction very fast will lose its energy and fall back down or collide with some ball and then fall down. But everything else will have a preferred direction of circle. Okay, now the system is stable already. Now this is the preferred direction. And then they have their own orbits. If I chop this cloth into half, I get the gravity well. Okay. So gravity, right, not only changes the space, the way space and matter interact, it also changes the way time interacts. So if you watch the movie Interstellar, it will tell you things like, I was waiting for you in orbit and 20 minutes down there was like 8 years up there or something like that. Can happen. It's theory, it's science fiction. Theoretically, we know it will happen, but we also don't know. No one has experienced before because we don't have the ability to send people to outer space close to the speed of light. But yeah, this is the age of human knowledge. Welcome. Previously, you're going from normal mechanics and gravitational energy to this one. Okay, so that's it. We're at the end of the chapter. And let me go and take a peek of the recent May June 21 question that I downloaded and see for interesting things that we can try. Okay. Anyway, as usual, you can stop me anytime. We can look at May June 21. So I'm doing this because it's not in the collection. That's also because it's fresh, but the question is a standard one. So I'll give you a few moments to try it. Do you have it? Wait, I don't think you have the question paper yet. Because I'm in the midst of giving my students tests, so I don't want them to see the question paper yet. So I'll prop it up here for you. Question is not very long by itself. It's about 10 marks, which is standard ink. But I'm going to give me a sec. I'll upload the paper on Discord for you. Okay, so you can find it here under the PYQ section. You can try question 1. It's like a all-in-one question. Everything tests a little bit, but didn't go very deep. There are also other questions which test a lot. All right, so it's also a good time to take a short break. So 10 minutes to try the question because it's 10 marks, and also 10 minutes to, I guess, stretch your legs if you need to. I will pause the recording. Not, you will see 10 minutes of silence. She sounds like a parking machine. Okay. Right, so let's mark together, or mark what you have done so far. Okay, so we're still given dimensions about the Earth. Okay, so let's think about how Cambridge structure that question and how you can use their structure to help you with unstructured question, like an entire big 7 or 8 mark essay question that was given to you in your test. Okay, so it always starts with the definition so that people know what you're talking about, but they will give you information. They will set up the question. So we have the Earth assumed to be an isolated uniform sphere with this mass, I'm just going to call it m. A satellite of mass small n is in a circular orbit. So immediately, normally, all these are clues to trigger or to prime your brain to think about information that you have already studied. So in an essay question, if I'm writing an essay question, I will give very little prompts. That means you have to prompt yourself. That's the difficulty of an essay question, okay? But anyway, you're given a circular orbit, so you know somewhere along the line, you may or may not need to use this, probably yes, okay? Period of the orbit is 94 minutes. Well, this is a pretty fast circle, okay, sure. Define gravitational field strength, so G. So this is force per unit mass. So just the term force per unit mass will get you 1 mark. Okay, next, calculate the radius of the orbit of the satellite. Well, like I said, centripetal force is equal to gravitational force. So they will ask you to explain anything, so I'll just proceed with writing the equation. There's period, so I'll use mr omega square is g mm over r squared. Okay, some basic housekeeping means I can find r as gm over omega square, right? Also, omega is 2 pi over t. So I can use this. So r will be gm over 4 pi square over t, which is times t squared here. So substitute 6.67 times 10 to the power of negative 11. Mass of the Earth is 6 times 10 to the power of 24. T square is 94 minutes times 60 squared divided by 4 pi squared. Testing the calculator. 4 times 60 squared. I got G M Oh no, this is R power 3, right? Can cancel like that, right? Power 3. Okay, the rest seems fine. So R cubed will be 3.2246 times 10 to the power of 20. Not writing the intermediate numbers are also okay. So answer power 1/3. So 6.85 or 6.9 times 10 to the power of 6. Can write your answers into SF for Cambridge. Okay, marks. Here is 1 mark. Okay, and also at the same time, if there is the right substitution here, here, and here, including the 60 here conversion, you get 1 mark. And then the final answer is bonus. Okay, so if you, whenever you get a value of R, you can always cross-check and see whether it makes sense or not, because you know if it's too big like this, that means you've forgotten to cube root. All right, so rockets on the satellite are fired so that the satellite enters a different circular orbit. So the satellite is going to move from one orbit to another orbit, but thankfully they are still circled, so we don't get the ellipse action going on. Okay, but this period is now 150 minutes. The change in mass of the satellite may be assumed to be negligible. Okay, so when this rocket is fired, right, what is going on is that it is there is a change in momentum. It's a bit like the rocket question that you get in your paper 2. The rocket releases gas and then pushes it forward. So this rocket is fired means there is work done on the satellite by the explosion, controlled explosion of the rocket. Okay, but doesn't matter. So this is your Earth. It has a circular orbit here, and then it jumps into another orbit. I don't even know whether it's higher or lower orbit, but this is a new radius. This is T. So basically I have R1, which is the first radius, 6.9 times 10 to the power of 6. T1 was 94 minutes. Okay, 94 minutes. This is the first radius. And then I now want to find R2 when my T2 is 150 minutes. So we have to come up with a relationship between R and T. So the best way is to trace back. How did you find your R from the first period, 94 minutes? Because we are still talking about the same planet. So the mass is the same. G and pi is always the same, so we don't even need to think about it. So from here, I can see R cubed is proportional to T squared. So if you're afraid that you cannot suddenly use it and show it here, then you just copy the equation from there. R cubed is equal to Gm over 4 pi squared times T squared. So it's the same planet, so hence R cubed is proportional to T squared. Then it is possible to write something along the lines of R1 over R2, or 6.9 times 10 to the power of 6 over R2 power 3 will be equal to 94 over 150 power 2. You don't have to convert this to seconds because you convert on top, you convert below. If it's multiplication, they cancel out. Okay, so let me ask my calculator what this number is first. Let's go power 1, 2, 6.9 divide by answer. So my R2 is 9.4 times 10 to the power of 6 meters. 9.422. proven. So 1 mark is this. Okay, and then the other mark is here. When you show the right substitution. You might be thinking, teacher, can I calculate? Like I put back in the equation. I put back in this one because I have M, which is the mass of the planet. I have T, which is 150 minutes. Then I find R cubed can. You can also substitute from scratch. Also can. But I like ratio. Ratio is my best friend. Okay. So, or if you directly substitute, you have to know that this ratio method, because sometimes they will give you information in graph, sometimes they'll give you information in a table. If you have done enough past year question, you know that sometimes you have enough information to directly substitute. If not, then you have to use ratio, because ratio allows you to find the period without knowing the mass. Of course, you could say, nah, teacher, I use the first set of value to find the mass law and then substitute into the second set of value law. Okay, sure. More steps. All right. Part 2, state with reason whether the GPE of the satellite increases or decreases. So we can tell right now that your radius has increased. Higher orbit. So we know GPE increases because the separation between the satellite and the Earth increases. So just to be safe, don't just say because R increases, explain what R is, which is separation between the satellite and the Earth. Okay, or another allowed explanation would be, you mention something like the satellite moves against gravitational force. Hence, GPE increases due to work done on the field. Actually, this is a better explanation, but they also allow the first one, which is easier to write. Okay, so it's a bit like, for example, if I push up my calculator, I am moving the calculator against the weight or the force of gravity because I'm doing work on the gravitational field. I do work on the field. The rocket explodes so that the satellite can get pushed up. It's like I put a tiny bomb in my calculator here and then I trigger the bomb. Calculator will fly up like the Coca-Cola bottle rocket. Not that simple, but very similar. Okay, last one. Determine the magnitude of the change, well, of the GPE. That's a very nice one. Okay, let me show you where the marks are. This one you will only get 1 mark if you got mentioned increase and a reason. No reason, no mark. Okay, magnitude of change. So get your first mark first by writing GPE is equal to negative GMM over R. This is 1 mark now because it's 3 marks. Hence, change in GPE or change in EP is equal to negative GMM over R1 minus negative GMM over R2. So I can factorize, with or without the negative sign doesn't matter. This will be R2 minus R1. Okay, we can substitute. Change in GPE is 6.67 times 10 to the power of negative 11. Mass of the world, the Earth, is 6 times 10 to the power 24. Satellite is 1002. Okay, and then we'll multiply by the two different radius. So to get a positive number, because I tell you what, I'll just minus so that you can see the increase. Increase? No, not the increase. So R2 is the final state. Final state is this one, 9.4 times 10 to the power of 6. Minus the initial state, which was 6.9 times 10 to the power of 6. So this 10 to the power of 6 can pull out also. And if you learn to pull it out, your life will be a little bit easier. To you, 6 times 24 times 1200. So when I say pull out, I mean factorize 10 to the power of 6 in your calculator. Divide by 1e6. Minus, multiply. Okay. 1 over 9.4, because I factorize out the 10 to the power of 6. So it's divided by 1 times 10 to the power of 6 minus 1 over 6.9. Okay, ta-da. So I'll get 1.85, 1.9 times 10 to the power of 10. 1.9 times 10 to the power of 10. So we just want the magnitude only now. So the magnitude or the change, you can even just omit the sign. So at this point, even if you omit the sign, it's all okay. Because when I see magnitude, you can throw the sign away already. But if you just want to stick to it, you can do so. Okay, second mark is when you substitute all these things inside correctly. And then you arrive at this one. Sign optional. Okay, let's look at your test question. Only this one got problem, the rest okay.
Sorry, Miss Liz.
Yes.
I have a question. So for the change in GPE, final minus initial, right?
Final minus initial. Yes.
So is it okay if I write negative GMM over R2, then minus negative GMM over R1?
Yes, perfectly fine.
All right, thank you.
Okay. In fact, that is the more disciplined way of writing. I will comment that. So change lah. We just change the position of this and this. Okay. This one. Okay, so when you're given a 7-mark question, right? Basically, you expect a lot of steps, right? It's an essay question. So 1A is still the same, force per unit mass of a mass placed at that point. Okay. So if they give you information, the first thing I'll do is I'll doodle, I'll draw, because I need a drawing to help me brain the question, right? So we have moon, we have earth. Okay, well, earth here, moon here. And then I'm given like the mass of the moon, 7.4 times 10 to the power of 22. And the radius of the moon is 1740 times 10 to the power of 3. The earth has mass 81 times. So this mass is 81 m and 3.7 radius of the moon. Okay, I'm just going to call this r. Okay, sure. The radius of the orbit of the moon is this one. So we know the moon is going to travel in some circular orbit around the earth. Wow, my orbit is so circular, I can't even. Okay, it's going to go travel like this. And the radius is the distance that we measure from center to center. So drawing diagrams will probably help you, unless you are the rare genius, brain the question or see it in context first. The distance. Okay, sure. By making relevant calculations, so for me, when I see this, I'm going to make a list already. What are the relevant calculations? using the data, okay, sure. Draw a label graph of the variation of field strength with distance. So I need to calculate a bunch of stuff so that I can find gravitational field strength against distance between Earth and the Moon. Okay, so what I'm trying to draw in a rough sketch is 1G, I want R, so a big question mark here. Okay. So sometimes, or most of the time, if the essay question is constructed properly, like this one, the definition is a hint about what you should look at. So the gravitational field strength is force per unit mass. So I am looking for what is the force per unit mass along Earth to Moon. Okay, so maybe I put a unit mass here, 1 kg here. And I ask myself, I wonder what is the force per unit mass on this little 1 kg rock at an arbitrary distance, which means at any distance r. So of course, then the logical thing to think about is, well, the Earth will attract this one. Okay, force of the Earth. And the Moon is also going to attract this force of the Moon. And there will probably be a point somewhere as I drag this 1 kg along for a fun ride between here and here, where the force cancels out. Okay? You can do this thing called testing, which is like what you tend to do in maths. Now you want to sketch this graph. You don't know how even the graph look like. Is there a turning point? So there are a few ways to approach this. Okay. Now I'm approaching this from the conceptual way. Concept. So we want to know what is the force per unit mass. So I'm going to take the unit mass and plug it at different places. Of course, when we are very close to Earth, the gravitational attraction of Fe will be very, very big. Whereas the gravitational force of the Moon is just very tiny here. Whereas at this point, Moon will be big and Fe is small. Okay. So there are a lot of calculations that I probably need to do. For example, I need to know what is this. Because here, the force of the Earth is very strong. So I need to know what is doing with this. I also know, I need to know what is the force per unit mass here, what's the force per unit mass here, and what's the force per unit mass along the points. So in order to sketch a graph, I need to know in maths, right, I need to be able to know the important points and also where does the domain begin, which is the surface of the Earth, and where does the domain end, which is the surface of the Moon. So I probably need to find G on the Earth. Probably need to find, I guess, G on the Moon, surface of the Moon. And I need to know the shape of the graph or what is going on here. Another hint, right, about your concept is that if force is a vector, and you can see I draw direction, meaning there's a pulling on the left and there's a pulling on the right. Naturally, they will spawn a point somewhere in between these two where the force will cancel out, looking for the equilibrium point. The push and pull between reopening the country because the economy is dying and people's mental health are affected versus people are dying from the virus spread. Push and pull. So there has to be like some sweet spot in between one because they're acting in opposite direction. You get the point. So I probably need to, number one, calculate, because I don't know how strict the syllabus is when the person starts this paper. So if this is a Form 6 paper, what I will say is calculate everything. Find the gravitational on the surface of Earth. Can I assume it's 9.81? No. Calculate, show calculation, very fast one. Find gravitation on the surface of Moon. Find gravitational field strength where Earth is equal to Moon. 3, confirm need to calculate 1. 1 and 2, I don't know. Because I don't know the nature of the syllabus. If it's Cambridge, I tell you no need, but the nature of the syllabus, I don't know. Okay, so in this case, we calculate everything. No problem. So gravitational force on the Moon surface is easier to calculate because On the moon surface, you will take G of the moon minus G of Earth. Teacher cannot ignore Earth. Cannot, we got enough data, cannot ignore already. Is it significant? We'll see. Okay, so gravitational force of the moon on the surface will be G mass of the moon over radius of the moon square. Okay, and then gravitational force of the earth would be, okay, this one I feel that is a bit too much. It's the definition of extra, but let's see if the numbers are big or smaller. Okay, so I can find force per unit mass of the moon because I will just take mass of the moon divided by the radius because it's on the surface. But if I'm considering the field of the earth, then I will take this distance because I want to find my I need different color. My point is here, right? So for moon, no problem. I can take the radius of the moon. But for earth, I need to take this distance. Which means it is 4 times 10 to the power 8 minus the radius of the moon. Sine. 4 times 10 to the power 8 minus radius of the moon. You don't this is mass of the earth. You don't gung ho and open bracket substitute value. Okay. So this one, 6.67. Now, normally I would factorize, but because I want to know how big GE is, so that I know if I really need to do this again for the Earth. Actually, I don't know. I will probably just do both so that I don't lose any marks because I don't know where the 7 marks are. Okay, so this is G. Mass of the moon is given. Let's deal with a bit. 7.4 times 10 to the power 22 kg. Divided by radius of the moon is 1740 times 10 to the power of 3. Okay, divide and conquer. You press for me. I want to know separate terms what they are. This is 81 times the mass of the moon. Is Earth that big? Okay, 81 times. Okay. Divided by 4 times 10 to the power 8 minus 1740 times 10 to the power of 3 squared. Normally, we assume that it is far enough and it's negligible. But is it though? I don't know, man. I calculate now. So normally Cambridge will tell you, oh, it's negligible. Or they won't even give you enough information to calculate. So you can sendiri neglect it. So 40 times 10 to the power 3 square. 1.63. Times 81. 7.4 divided by minus 174. Okay, so this is 0.0025. You ignore or not? 252. I think negligible lah. Cause round to 2 SF no more already. So I write 1.63, okay? But I will still show this calculation sebab takut hilang marker. But if you think your teacher doesn't need this, I don't know, you need to figure out. I just tell teachers, I just tell students, it's too small, neglect. So if the heavier earth is already so small at the surface, can I assume that when I repeat this to find the gravitational force of the earth on the moon, the gravitational force on the earth's surface, sorry, that the GM will be very small now. Because now we are taking the Earth's surface, right? So this will be gravitational force of the Earth minus the moon. I'm looking for the magnitude now, okay? We will set up the direction later. So in this case, if I take GE minus GM, this one, I copy the substitution, right? Will be G 81 times the mass of the moon divided by the radius of the Earth square. So radius of the Earth, if we trace back here, 3.7 R, okay. 3.7 times 1740 times 10 to the power of 3 squared. Of course, you could say, teacher, I can use ratio, can. You can ratio with 1.63. But I already keyed in my calculator, so I just press reverse button. I can input all this value. I get 9.64. GM is negligible when rounded to 2 decimal points. This one, I don't know. What is the common practice of your teacher if you want to get marks from them? Do they want you to explain this or just ignore nicely, or you explain? Just see whether you just, I don't know your teacher.
I also don't know, man.
Okay, never mind. Does he or she give answer?
I can't know.
No.
Discuss it in class.
Okay. So I'm being extra here. Normally this one all I tak kira lah because it's so small. It's so far away. Come on. So if I look at the moon surface, the heavier or the more massive Earth is already negligible. Meaning if I stand at Earth, the smaller moon is even more negligible. Does that make sense? Because Earth is the heavier one. Okay, so I got 1.63 and 9.64. Why isn't it exactly 9.81? I don't know. Estimation. Okay. But the important must-do calculation is there will be a point in between the Earth and the moon where the gravitational force cancel out because one is pulling towards the moon, one is pulling towards the Earth. So when GE is equal to GM at X, so we want to find X. So gravitational attraction of the Earth will be G, mass of the Earth over X squared. Because all of the distance right now we are measuring from X. So maybe there's a point here to here is X now, where FE is equal to FN. Okay, that means, so we can measure from here to here. So this means here to here will be 4.0 times 10 to the power of 8, the whole thing minus X. Basically, what we did here. So G, mass of the moon, 4.0 times 10 to the power of 8 minus X. I can cancel this. I will have mass of the Earth divided by mass of the moon is equal to bracket X squared over 4 times 10 to the power of 8 minus X. I mean, this whole thing squared. Mass of the Earth is 81 times mass of the moon. So this is 81. But I can bring the square to square root here. That's why they give you a nice number, I guess. So always do this square root method. You don't go and expand this and then get some weird partial fraction to give yourself some partial headache, because this is much easier to solve. Okay, so I'll continue moving this around. 9x will be equal to 9x 36 times 10 to the power of 8. It's equal to x. Okay, so 36 times 10 to the power of 8 will be equal to 10x. Numbers are nice though. You gotta give your teacher that. X will be 3.6 times 10 to the power of 8 meter. So at this point, GE is equal to GM. So if you look at your point mass, one is attracted to the moon, one is attracted to the Earth. Earth is here, moon is here. So the forces will cancel out, or the gravitational field will cancel out because they are vectors and they act in opposite direction. At 3.6 times 10 to the power of 8. I think we have more than enough to draw. So if I am writing a mark scheme, you see, because they give you this value, right? All these values, it's actually a bit more prudent to sketch everything out. But again, I don't know how strict the sketch should be. Never mind. We shall just assume the most strict condition possible. I change to boxes. So the Earth is 3 times the radius. Does your teacher care about this? Also don't know.
Yeah.
Do they communicate that? Because I will, or depends. I don't really care. As long as the Earth looks bigger than the moon, I'm fine. But okay lah. It's about 4 times. So let's assume this is the radius. The radius is 4. It's very big. Something like this. So this is the Earth-ish, kind of. And then somewhere here we have a moon, where the radius is about 1. Okay. I am still estimating, but it's a more reasonable estimate because now I have boxes now. Okay. But the separation between them is 4 times 10 to the power of 8. Okay, to do some quick calculation. Times 10 to the power of 8. So what I'm trying to do here is to know how far away do I park the moon. This one don't need to show lah. This is just for your sketching. About 300 times the radius of the moon. I mean 229. If I take the radius as 1 box and I park this at 229 box, dude, okay lah, definitely not possible. Okay, so you just push it at a reasonable distance now. Don't care already because it can't fit on the graph. No fit. So ideally, you should know if, let's say, you didn't score a point, what you need to do to get that point. But currently, we have done all the calculation. So when your object is here, gravitational attraction of the Earth dominates. So this, let's say we take this direction as negative to the left. So it's going to be negative 9.64. There, what unit for you? kg per Newton. Okay, so 2, 4, 5, 9.6 is somewhere here. So negative 9.64. I guess I could put 3.7 radius of the moon here. Okay. And then somewhere here at the value of this, you will get 0. It will pass the x-axis. However, at this point in time, it's just about how accurate. Do you want a real plot? Do you just want a sketch where it's not drawn to scale? I don't know. So I think because it's not drawn to scale, I'm not going to label that. But what I will label is that this point here would be 4.0 times 10 to the power of 8. So if this whole thing is 4.0, okay, Cambridge is very nice one. Anything more than 2/3, you are okay for this sketch. But this one, this 3.6, 4.0 is 90%. Okay, hang on. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 22, 24, 25. So 90% is 2.5. So maybe somewhere here. Ish. 2.5 boxes on the other side. So this would be 3.6 times 10 to the power of 8. So first, gravity is going to be very, very strong. As you travel further away from Earth, the gravitational field will decrease in the opposite direction until it reaches 0 here, and then it will increase. Increase until how much? Positive 1.63 on the moon's surface. Because why? When something is on the moon, oops, the gravitational force of the moon will dominate. Of course, because the moon is very light, so it's not going to be like very strong. So 1.6 is about almost 1 box like this. Paper here. Positive 1.63, something like this now. Correct already. Well,
Thank you, Miss.
Sorry, cannot reach here. Reach the surface. I think don't need to draw inside. No one gets any marks. You go and look at the good student and see how your teacher mark him so that you understand the mark scheme. But Cambridge won't do this to you. You know that everyone's 0 already. So what you could do is you could review back when we did this question, okay, and see how they structure the question differently. They've drawn this for you. They also give you all the relative in ratio, but it's with respect to something else. But also at the same time, right, they ask you to explain first. They conceptually explain, then calculate, then sketch, which was what I did for this question, but you will not be awarded marks for. Remember all the planning we did here? So that's the difference between a structured question and an essay question. And we know the ideas are hard, so I think it's okay to structure it, but yeah. Or you can just teach your brain to structure it that way, if you understand. Okay, that's it. Any other questions from the floor? Are we okay? I'll be seeing you all tomorrow, right? Right? Am I seeing people tomorrow?
Yeah.
Okay.
Yes, Miss.
All right. So tomorrow I'll just continue from 13 to the next chapter in your syllabus. Okay. And I'll put up the notes today for you to print out if you are the hard copy kind of person. So yeah, my only comment to that is if you see this kind of self-mark question and you cannot do either in your homework or in your class test, just throw them inside the Discord. I can comment on them as well. Or I can give you hints. I structure it for you, then you try your own. Okay. All right, that's it. I'll stop recording now. Please